Hello. Today we're going to start a new chapter, which is the first law of thermodynamics. The first law of thermodynamics is about the conservation of energy. And if energy is conserved in total, it still can be transferred between one system to another. And so if one system is going to lose energy, the surrounding is going to gain energy. And so before we can start to talk about conservation of energy, we first need to well define the system and also how we're going to account for the energy transfers. Let's consider an example. Let's say you have a cup at 20 degrees Celsius and you add coffee at 70 degrees Celsius. The coffee is going to lose heat, and this heat is going to be partly transferred to the cup, and so the cup is going to gain heat. By convention, if you have a system, we're going to choose the heat added to the system as a positive number. So for the cup, which is gaining heat, Q is going to be positive, and for coffee, Q is going to be negative. Sometimes the system can do work on the outside, and by convention, we're going to choose the work done by the system as a positive number. Let's look at an example. Let's say that you have a block that is sliding on a surface. The surface is going to exert some friction forces on the block. The friction forces are opposite to the displacement, so the work done on the block is negative, which means that the work done by the block is positive. So if your system is the block, the work done by the block is going to be positive. An important case to consider is the work done when you have a change of volume. Let's say you have a cylinder with a piston and gas inside the cylinder. If the gas is expanding, there will be a force on the piston that is towards this right direction and a motion of the piston that is also towards this right direction. So the work done by the gas, in this case, is positive. Now let's say that the piston is not moving. In this case, if there is no displacement, then there is no work. That doesn't mean that there is no forces, right? You still have the molecules of the gas that are pushing the piston, and so there is a force still exerted by the gas on the piston, and this force is equal to the pressure inside the gas multiplied by the area of the piston. Now let's say that my piston is moving by a quantity dx. Then the small amount of work is going to be equal to the force multiplied by this displacement dx, which is the force P, the pressure multiplied by the area, times dx, and A multiplied by dx is the same as the change of volume dV. So the small work is going to be equal to P dV. And if I want to get the total work along a total displacement, I can integrate this, the integral between volume 1 and volume 2 of P dV. So remember this result. The work done during a volume change is the integral between the initial volume and the final volume of P dV. This is a formula, but there is a graphical method to see about the work done by the system. Let's say that you can represent the state of the system on a pressure versus volume diagram like this. And let's say your system is increasing volume and at the same time decreasing pressure. So the work done between volume V1 and V2, V1 here and V2 here during an expansion is going to be represented by the integral below this curve, so the red region on this graphic. So in this case, the work done by the system, by the gas, is positive. Now let's say that instead of an expansion, it's a compression. So the volume decreases and the pressure increases. In this case, V1 is on this side and V2 is on this side. The area remains the same, except that now the work done by the system is negative, right? There needs to be some work done on the system for the gas to compress and reduce its volume. Any question? Yes, what about when the volume doesn't change? Good question. This would be, for example, if you have a gas in a box and you increase the temperature, so the pressure will increase, but the volume is fixed by the box. So on this diagram, pressure and volume, you would have a vertical line like this from a low pressure to a high pressure, but at a constant volume. In this case, the volume is constant, and so there is no displacement, and the work is equal to 0. Indeed, the area below this curve is equal to 0. You can also have an expansion at a constant pressure. So in this case, the pressure stays constant and the volume changes from V1 to V2. And so we have an horizontal line like this on this diagram. And in this case, the area below this curve is this rectangle here. And so one can calculate it as the pressure multiplied by the difference of volume V2 minus V1. Now let's do an example where we have to use this formula, the case of an ideal gas during an isothermal expansion. So in this case, the temperature doesn't change, and we have the pressure of an ideal gas given by nRT over V. So on a diagram, pressure versus volume, this would look like this 1 over V curve here. And the expansion between V1 and V2 would give a work done by the gas, that is the area below this curve. So how do we calculate this? Well, we apply the formula, the integral between volume 1 and volume 2 of P dV. We can replace P by nRT over V, this is gas law, and then since nRT are constant, this is isothermal, constant temperature, so we can take them out of the integral, and we have nRT, the integral of dV over V. Now, a primitive of dV over V would be the log function, and so we have nRT log of V2 over V1. And since this is a isothermal expansion, T is constant, and so I also have P1 V1 is equal to P2 V2. And so I can replace V2 over V1 by P1 over P2, and so I have also nRT log of P1 over P2. So if you're given the two volume and the temperature, you can calculate the work this way. If you're given the pressure, initial and final, you can calculate the work using this formula here. An important aspect about the work is that it depends not only on the initial and final states, but it also depends on the intermediate state. So it depends on the path that you take for your system to go between one initial state to one final state, right? So for example, if you have an initial state on the PV diagram here and a final state here, the work is going to be different whether you use this path here, first a constant pressure and then a decrease of pressure, or if you use an isothermal expansion like this, or if you first decrease the pressure and then increase the volume like this, right? So along those three passes, the work is going to be different. We can look at this again. In the first case, the area below the curve is going to be given by this large rectangle here. So this is going to be the work. In the second case, an isothermal situation, the area is going to be below this curve here, and so it's going to be smaller. And in the final one, it's going to be even smaller. First, the decrease of pressure, and then the increase of volume. The area below the curve is given by this function here. And again, if we do the transformation in reverse, first we decrease the volume and then increase the pressure. In this case, it's a contraction, and the work is going to be given by the opposite of the area below this curve, right? So the work is minus the area. And so finally, if one does a cycle from an initial state, increase the volume, then decrease the pressure, and then decrease the volume, and then increase the pressure, one does a cycle like this. In this case, the work is going to be the area inside this cycle. And so you see that the work is non-zero, even if the initial and final state after the cycle are the same. All right, I hope this is clear for everyone. Let's try a practice question. One more minute. The correct answer was C. For both paths ABC and ADC, the work is going to be positive.